Hello, welcome to part 2 of the video series Deriving R Squared. Today we continue with the prerequisites to the main derivation. We will discuss data, what the mean of a data set is, and what the variance of a data set is. So let's start off. Our first topic to discuss is what is data? So before I explain this concept to you, I have a few numbers written down on the screen. Just have a look at them. What do you think these numbers symbolize? What do they mean? Just think about that. Now, to me, if I had seen these numbers for the first time, I would first of all think that they're just random numbers put in front of me. The next thing I'd see is that, okay, they're sorted. There are 3 ones, there are 2 twos, but it yet wouldn't make a lot of sense to me. Okay. Now, what if I told you that these numbers over here are actually the prices of houses. I'm going to write this down. Prices of houses in the city of Bangalore, in Bangalore or Bengaluru, which have a unit of 10 lakh rupees. This means that this first value over here, 1, represents a house that costs 10 lakh rupees. The 2 represents a house that costs 20 lakh rupees, and the 90 would represent a house that costs 900 lakh rupees or 9 crore rupees. Now, after you've been given this knowledge that these numbers represent the prices of houses, your mind would immediately start working. So you'd start looking at these numbers very differently. For example, you could say that given these numbers and these prices of different houses in Bangalore, the lowest cost of a house could be 10 lakhs, or as represented over here in these numbers, 1. The highest cost would be 199. The most frequently found houses, the most frequently found house costs of houses would be 1, right? And so on. You could make so many, you could understand so many things using these numbers now, right? This is the difference between data and information. A lot of people get confused and think that data and information are the same thing, but in fact they are not. When you saw these numbers and they were just random numbers to you, they did not make any sense. That's when these numbers were data. But as soon as you started analyzing them and understanding, oh, these are the prices of houses, the lowest one I can find, the lowest cost house I can find in Bangalore would be 10 lakh rupees. That's when this data started giving you information. So it's more like saying that data is raw facts and information is what you extract from these facts, how you analyze these facts and get knowledge out of it. Okay. Now, another thing that I'd like to discuss about data is this, that there are 2 kinds of data that we'll discuss, which is prevalent in the field of probability and statistics. There's sample data and there is population data. Now, what does this mean? What if I told you that you had to get data for every house that exists in the entire country of India? Would it be simple to do that? Not really. Finding every single house's prices, you'd have, first of all, collecting the data would be very tough. Second, it would be uh, very difficult to sort these prices, to store these prices, everything. And then you would find places where you might not even get the exact price of the house. Therefore, in these sorts of cases, we use something called sample data, which means that we select and get the costs of houses in certain areas, not the cost of every single house, but the cost of a few houses. Therefore, generally, we use sample data instead of population data because population data is very tough to gather. Another example would be that let's say a scientist in America is trying to research sleep patterns of people. Would it be easy for him to find out the sleep patterns of every single of the 9 billion plus people on Earth? Not really. Therefore, he or she would take a few cases, they would take a few people from here and there and observe their sleep patterns for their research. Okay. Now, the next thing I wanted to discuss was this, that we noticed this data that I had shown you, we created some uh, observations on it. We we analyzed it and understood a few things. Now, what if the data was not just 10 numbers, but instead I gave you about 10,000 numbers of the data of 10,000 houses in Bangalore? Would it be easy for you to analyze? Number one, here the numbers have at least been sorted by me for you. But generally, when you get data, they are not automatically sorted. So they're all jumbled up. Now just think of 10,000 numbers all jumbled up. It is not an easy task to actually analyze those numbers then. Hence, we have mathematical tools that help us understand this data better without having to actually go through each line of data or each number in the data. Okay. The first mathematical tool that we are going to discuss is called the mean or the expectation of a data set. Now, why did I say data set? Data set is basically a set of numbers. So here we had about 10 numbers. The whole set is called a data set. Okay. Very straightforward meaning. Okay. Now we come to the mean or expectation. You can see a pizza, the picture of a pizza. I am extremely fond of pizza, so I thought what's better than to have an example based on slices of pizza. Yeah. Okay. Now let's say I told you that there are 8 people and there are a total of 24 slices of pizza. Okay. According to you, now think of this, okay? You can pause and think of the question too. Think of this. What if I asked you now 24 slices of pizza for 8 people, okay? Let me just write that down. According to you, what is your expectation that how many pizza slices would each of these 8 people get? Your immediate expected value. What do you expect? So generally a person would say 3. Why? Because you would assume that these 24 slices of pizza are being equally divided amongst the 8 people, and 24 divided by 8 is equal to 3. Now let me tell you the actual distribution. So the first of these 8 people got 5 slices of pizza, the second one got 4, the third one got 2, the fourth one got 3, the fifth one got 1 slice, the sixth one got 6 slices of pizza, the seventh one got 2 slices of pizza, and the eighth one got 1 slice of pizza. Okay. Now, have a look at this. Is it equivalent to your expectation? Not particularly, because only one person actually gets 3 slices of pizza. But that number 3 helped you understand a basic sort of expected number of slices that every person could most probably get. And if you notice, every person has gotten slice of pizza that surround this number 3. So if you think of the number line, 3 would come here, and this is where you'd have 2, 1, 4, 5, 6. So all these numbers surround this number 3 that you expected. This number 3 is also called the mean, or in probability, it's even called the expectation of a data set. Okay. Now the expectation is also represented, or the mean is also represented as X bar for sample data. Remember, it is for sample data. For population data, it would be represented as mu. Okay. Now, let us try and find out the mean of the data set we saw previously. So to calculate that, what you'd have to do is first sum up every single number that you have over here. So that would be 1 plus 1 plus 1 plus 2 plus 2 plus 6 plus 90 plus 140 plus 148 plus 199, and you'd have to divide this entire sum by, any thoughts? By 10, because there are 10 house prices that we have over here. Now this value is equal to 59. Therefore, you could say that the mean price of houses in Bangalore based on the data set that we have is 59 or 5 crores 90 lakhs. Okay. Now, the next thing is this. Let me represent these values in a different way. Okay, I'm going to try and write it differently. So just let me scroll down a little bit. Okay. So now this, the earlier price could have been written as 1 times 3 because 1 is occurring 3 times, plus 2 times 2 because 2 is occurring 2 times, plus 6 times 1, plus 90 times 1, plus 140 times 1, plus 148 times 1, plus 199 times 1 divided by 10. Now this could further be written as 1 times 3 by 10 plus 2 times 2 by 10 plus 6 times 1 by 10 plus 90 times 1 by 10 plus 140 times 1 by 10 plus 148 times 1 by 10 plus 199 times 1 by 10. Now if you notice over here, what we've done is we have written the price. I'm going to change the color. 1 second. Okay. So we've written down the price, and then this value is also the probability of getting that particular price. So if you notice, because 1 occurs 3 times out of 10 times, this has a probability of 3 by 10, which is equal to 0.3, or in percentage form, you could say it's 30%. Now, if you rewrite this as a small term, it would be the sum of this symbol symbolizes sum. Okay, it's called sigma. The price times the probability of the price. So the probability of that particular price. Okay, and this is the expression that symbolizes expectation in probability. I just wanted to introduce this concept to you. You would understand this better if you studied probability, but just as an introduction. Okay. Now, on the side, you can see another set of numbers, right? Let's have a look at these numbers. Each one of them is 59. So let's try and find the mean. Okay, we add all of these together. If you add 10 59s together, it's kind of like saying 10 times 59, right? And we divide it by 10 because there are 10 values over here. And this is merely equal to 59. Now, think of this. In the first data set also we saw that 59 was the mean. In the second data set also the mean is 59. But are these two data sets the same? Let's think about it. Okay. The first data set says that the mean 59 lies here, for example, and you have 199 over here. 1 second, I'm not able to write it. 149 say over here. sorry, 148, 140. Okay, then you have 90 somewhere here. Okay, then here you have 1, here you have 2, 6, and so on. Okay, now this is how the number line looks for the first data set. For the second data set, everything lies at 59. So do you notice that in the first data set, the spread of the numbers is more, the range of the numbers is more. But in the second data set, it isn't. It's very less. It's actually just 0. Therefore, the data sets are not the same. This also tells us this, that just finding out the mean of a data set does not give us enough information about the data set. It gives us a little bit, it gives us a basic understanding of the data set, but does not give us enough information. Therefore, in these cases, we can also use another mathematical tool called the variance of a data set. So let's discuss that. We said that the spread is very important of a data set, right? Now to calculate the spread, how would we do it? This time we'll try and find the average of the distance between each data point. Data point means every value of data that we have. Okay. The distance between each data point, I'm just going to write it as dp, with the mean. Okay. We'd find the average of these distances. Therefore, if you think of it logically, the distance between the mean and each value that we get in that data set, an average of that would give us a basic understanding of how far away each data point is from the mean of the data set. Okay. Now to do that, so this is represented as S square. That's the variance. Okay. The variance of population data would have been represented as sigma square. Here we'll write S square because this is just sample data. Now S square is equal to the sum of the distance between each data point. So I'll represent each data point value, that is 1, 1, 2, 90, all of them as D, from the mean or X bar. And this entire sum is divided by the total number of data values that we have, which we can represent by N. Now this is where we may face some issues. The first thing is this. If you think of it, let's look at two data values that we had in the Bangalore city data set. We had 1 and we had 90. Okay. Now X bar is equal to 59 in this case. 1 minus 59 will give you minus 58, a negative number. And 90 minus 59 will give you a positive number, 31. Okay. Now think of this. If you add negative and positive numbers together, you might get a very different average. We don't want these negative and positive signs to affect the actual value of the average. Therefore, to not face this issue, we square the distance. Why? Squaring helps make everything positive because any negative number squared gives us a positive number. Now, some would say you could use something called a modulus, basically getting the positive value only. The problem with that is the differentiability of that particular graph. I won't discuss that right now, but maybe in a later video I will. Okay. So for now, just think of it in this way. We don't want the sign of the distance to affect the actual result. Okay. Now the second thing we do is that because this is sample data, we subtract n by 1. If it was just n, it would work very well for population data. But when it comes to a sample, statisticians have seen that n minus 1 helps in getting a better approximation of the variance or a better value that describes the average distance between each data point with its mean. Okay. Now let's try and calculate this variance for our Bangalore price data set. Okay. I'm going to write it. I'm going to use a different color this time. Let me use green. It's a nice bright color. Okay. So, 1 second. Okay. So, given the definition of the variance, what we'd write is 1 minus 59 the whole square plus 1 minus 59 the whole square. It happens 3 times. So I'm just going to multiply it with 3 over here. Plus 2 times 2 minus 59 the whole square plus 6 minus 59 the whole square plus 90 minus 59 the whole square plus 140 minus 59 the whole square. Sorry. Plus 148 minus 59 the whole square plus 199 minus 59 the whole square. And based on our earlier definition, we divide this by n minus 1. So here, because we have 10 data values, 10 numbers, we divide this by 9. Now if you calculate this, this is equal to 6049.11 approximately. But does the 6049.11 give you a good understanding? Doesn't make a lot of sense, right? Because our numbers are so close to each other. 6000 is so much bigger, and this is happening just because of squaring. Therefore, we have something called the standard deviation, which is basically the root standard deviation, or S, because that's S square. Variance is S square, so this is S. Standard deviation is equal to the root of the variance, equal to sigma in population. I'm just going to write it here this way, but remember S is not equal to sigma, okay? Which is the root of the variance. And in this case, S is equal to 77.776 approximately. So now what you'll notice is this, that 77.776 now makes more sense. You could say that if you average out the distance between 199 and 59 and 1 and 59 and all the other data values with 59, it makes sense that 77 is an approximate average distance between each data point and its mean. Okay. Now let's have a look at our second data set. What do you think? What is your guess? What's the variance of this second data set? The answer is 0. Because if you notice, every data point D is equal to the mean. This means that D minus X bar is going to be equal to 0. So every term that you're adding together is 0. Therefore, the entire variance is also equal to 0. And doesn't that make sense? Because as we saw in the previous slide, there is no spread of the data in the second data set. It is all these data points are clustered at exactly one point, right? Exactly in the middle where the mean lies. Okay, so this is it for today. I hope you have a wonderful day and a great week ahead. Thank you so much.